All right, we are here. We're live. Looks good. Hey, it's me. All right. Put that over there to the side. All right. Cool. Welcome back. How's it going? Hope you had a good week. It's nice to be back. I'm here. My name is Agent Ultra. If this is your first time tuning in, welcome to the stream. Here we hack on Haskell stuff. We're going to learn about wave function collapse this week, as we've been doing for the past couple of weeks. And yeah, we're going to have some fun messing around with that, learning about it, figuring it out. So, without further ado, I'm a little late starting this week. Sorry about that. Let's get everything set up and going. Let's get some editor action happening here. And all that jazz. Okay. Hey, tech support, great. How you doing? Thanks for tuning in again. Nice to see you. How's your week been? All right, there we go. Okie dokie. So let's open up our code and we'll get going here. Let's see, projects. I don't know. I want to open up the thing in projects, and we're going to wave function collapse. That's the one. Right. So last week we added patterns. Patterns. So what makes wave function collapse kind of unique, being just not, it's being a constraint solving problem, is that the constraints can be generated from the inputs. So you get a tiny little bitmap image, we cut it up into little patterns that we use, and the rest of the algorithm, which we're going to get to probably this week. Tech support says, just a lot of work. Yep. We got started with reading this book called Programming Language Foundations in Agda. That is a cool book. Let me know how you enjoy. I haven't gotten too far into Agda, but there's that and another book that I'm interested in. But I'm mostly, when it comes to theorem proving, I've mostly worked with Lean. I like that one quite a bit. But I'd be interested in knowing how your experiments in Agda go. So yeah, we got it all chopped up. Now I've done a little bit more research on this in the intervening time. I think there's a little bit more we could do here with patterns before we can get to the main stuff. Just a couple little helper functions. Maybe we want to do the symmetries and things like that. So we have a little bit more pre-processing to do, and then we can get to the main algorithm. Oh, cool. Yeah, I hear that other language is it's nice. Like, there's a lot of libraries for it, and a lot of work has gone into the ecosystem there, but it's still it can be fairly difficult to read. It's pretty dense. So, yeah, so that's what we got. We got fill pattern, we got fill patterns, driving out of textures. Textures is kind of like our, I don't know, baseline, some data type that you're going to map to, that we're going to map to when we write the other stuff, when we start integrating with SDL and on image libraries and whatever, all that stuff. All right. Okay. There's a couple of things. One, as I understand it, is that we don't need just the interior patterns from the texture. We could, symmetry pulse is blank. We're just talking about symmetries for a moment there. We could, and maybe should, take all of the sub patterns from the input texture, meaning that we could treat the texture as like a toroid and just wrap all the way around. And that will give us more subpatterns we can use in figuring out things. Hey Star RL, welcome to the stream. Welcome. First time, nice to see some new faces. So that shouldn't be too hard to do with the code we have here so far. I think what we would need to update to do that is one, we wouldn't actually need to calculate the number of patterns to stamp out. So like, it's kind of like a cookie cutter going into our input texture, going 1 pixel over at a time, 1 pixel over time, catching the overlapping sub-patterns of the input texture. We're just gonna, right now our algorithm starts at one edge and ends at the other edge. Right, by calculating the number of cookie cutter stamps we're gonna do internally so that we don't overlap. But we can actually go all the way around and wrap over the edge. And get all the sub-patterns that way. So basically for a 10 by 10 input texture, we should get 100 patterns. That's the general gist of it. Why don't we put that in a test and then we can just run that. So, no, sorry, I need to add, what do I need to add? I need to add some dependencies to my test. I need hspec. Can't remember if it's lowercase or uppercase. We could do this, we could express this as a property-based testing, so we could use quick check. And hspec, I think it has built-in support for quick check. Yeah, property-based testing. That's how you know you're doing it. Don't write individual tests, generate your tests. Although I feel like sometimes, like that's a good tagline for property-based testing, but I feel like that it kind of obscures what property-based testing is really all about, at least to me. I'm not sure if it is to you. Test.hspec. And quick check. And so our test here is going to be hspec. Do describe pattern. Zip. Now we're going to do a property test. This prop function comes from hspec's quick check integration. All overlapping patterns, I'll call it. Hopefully that makes sense to future me. We get an arbitrary texture. So I'm saying for any texture, we're going to, or even you can say there exists a texture. We're going to say that the number of patterns we get out from that texture could be equal to the square size of the texture. I don't know if we have a function already defined to get the texture size. We do. Yeah. So it should be texture equal to texture size tech times 2 squared. So I have to import those, of course. Algorithm dot wave function elapse. Yeah, let's get the builder building. I just use stack here as my build tool. Comes with a little handy test runner to run my test suite. We're going to use fast and file watch as we usually do. Fast just compiles without optimizations, so it's fast to compile. And file watch just reruns the test on every file change. Okay. Oh, am I not in the right directory? I'm not. Silly me. Yeah, hopefully I got all my dependencies set up right. Cool. Right, so we just need some parentheses around this, probably. Texture. Patterns returns a list, so that should be the length. And we might need to convert some things to integers, because length, I think, returns an int. Or to integral, from integral. So I don't know, something like that. Okay, prop. Okay, so we need an arbitrary instance for texture, of course. I haven't written one. And no instance foldable over function of word. So I might need to put this in parentheses just because of the precedence of inline functions, like should be. Oh, patterns needs another argument. That's it. Ba-doo-ba-doo-ba-doo. It doesn't matter, we could pick whatever. Yeah. Because if we pick 1 by 1 patterns, and we have a 10 by 10, that'd be 100. If we pick 3 by 3, that should still generate 100. 10 would be ridiculous. Up to, yeah, I don't know if you can go above the size of the texture, actually. So let's just hardcode 3 for this property. Maybe we want to get rid of that hard-coded number later. Okay, so we just need that instance, and then we should compile again and run that. Okay. Cool. So let's do that. I think I'm going to need to add quick check as a dependency to my library as well. Some people do it this way, some people don't. There's no right or wrong way. Basically, you know, I'm going to be importing quick check into my actual like code library and then creating the arbitrary instance here. That's basically because of the way type class instance resolution works in Haskell. Generally, you want the instance of for a particular type to be like in the same module as the type is defined for. Otherwise, you get something called the orphan instance warning. And some people take a pretty hard line on orphan instances. I'm not sure it really matters so much for us because we're not really, well, it's kind of a library, so maybe it does matter. And we should just be nice and do it this way. So anyway, let's not get too sidetracked about it. We just import quick check. Or is it test.quick check? Might be test.quick check. Yeah, okay, it's test.quick check. Cool. Then we'll make an instance for it. Instance. As long as we have an arbitrary instance for A, then we should be able to create an arbitrary instance for a texture of such A's. Okay. Is that how I spell it? Arbitrary. There we go. Okay, so the type class just makes you define this one function, arbitrary. And yeah, I'm gonna need a size, I guess, from it. So I have to look that up. Quick check. So I want to get the size that it wants, and then we will be able to generate it from there, I believe. No, not in this module. Where is it? Contents. Arbitrary? Shrink. Oh, what's the function called? There's a function to get the size it wants to generate. Isn't there? Oh, what was it? I think we had it actually at one point. Let me look at my logs. Oh, I squashed it down. Got rid of it. It's not there. Maybe it's in Gen. Anyways, as long as we know which size you want to generate, we should be able to do it. Okay. Get size. There we go. We can call it S. Get size. Okay, and then what do we need to generate a texture? We need to generate a fill texture. We need an arbitrary A, and that'll fill the whole thing with the same elements. Might not be super useful if we want to test symmetries and rotations later with this instance. Like, 'cause if they're all zeros, then no matter what rotation you get, you can't tell that it's been rotated. I guess it would be capable of arbitrarily choosing such a texture that is filled in with zeros. In which case, yeah, the symmetries there are going to be... The properties we could generate there for the symmetries would be hard to test. Although they would still pass, so maybe it's fine. I would just feel better if we had something like that. So we take up the size. Maybe what we could do is we could generate an arbitrary list with the right dimensions, construct the array, and then wrap that in texture. Infinite list of. I guess inference would probably be able to figure that out. So x's. We don't want an infinite list necessarily. We don't want a random length, we want a fixed length. Well, if we can get an arbitrary A and generate an infinite list, we can take the elements we need from it, given on the size parameter. So let's try infinite list out. And then we would return texture and array list array. That would be 0 to 0 to SS, size, and axes. Okay, I might not be able to infer what we want. Infinite list. Oh, did I just not spell it right? No. Infinite list of. Or it wants me to give the gen for that. Do I just have infinite list? I do. Okay, that's the one I want. Okay. Okay, so get size returns int. That's word, so we just need to renum that bad boy. Just reach into there and renum it that way. Okay, cool. We're back to here. Okay, so now our test just needs to... So the test can't figure out what the type should be. This is what this type error is saying. It's ambiguous. Right, so the callers are callers set types. And since we're getting this as a parameter, we have to tell it what type it needs to be. Right. Like what the A needs to be. So we can make this like int with type applications. I think. It might want me to not use that way. Already highlighting it. It's not a function. Application. Yeah, no, sorry. That's only for applications. We have to do scope type variables. So we'll say texture evidence. Really, it would probably be textures of like word 8s if we're doing RGB A, maybe. RGB, at least. Yeah, scope type variables, we need that one. There we go. Voila. Okay, this should fail as a test. If we've wrote a really bad instance, it's going to go off into forever. Yeah, and I think we did. We need to explicitly take so many. Oh, that's gonna be annoying. Let's see if that makes it compile. No. We didn't do. Okay. So this would be... Why would this be running infinitely here? Explicitly take so many numbers from x's. Pass that to a radial list array. Pop this into the REPL here and just play around with this. Sample. Yeah. Sample. Import desktop quick check. We got sample. Let's sample arbitrary. I gotta say I. Let's sample arbitrary texture of word. Did we not load this yet? Let's load it. Yep. That's why, maybe. That's a good indication that something's wrong there. This has to be list, at least list 1. But it should be infinite list, so... Array bounds. All that wrapped around, because, yeah, if it shows 0, 0, that's no good. Let's see. So if we generate a size, so S would be 0? So 0, 0. I'm taking S times 0 times 0 would be 0. Taking 0 elements from it would be an empty size, an empty texture. So we can't use get size because we can't choose 0 for an arbitrary texture. Or we have to special case that. Let's look at the implementation of list 1. List of 1. Okay, well, it chooses. Okay. So it doesn't use the size parameter. Okay. Oh no, it depends on the size parameter. It's using sized. Okay. Okay. Let me get the n as a parameter, which we called s. And then we can But then we would just want to take s at least 1. So we'll let n be our limit. And that will be a max of 1 or s. All right, and then we'll take the square of that from x's. this will go up to NMN. Right, and of course we want to enum those. Okay. We got at least an array of 0, 0. Well, that's an array of 2 elements. So if it's picking 0 again, then we get 1. Then 1 times 1 is 1. We take 1 element from X's, but array is going to be 2 elements. Right. So then this needs to be 2 enum n minus 1. There. Now we get an arbitrarily large one. Cool. That's better. Glad we fixed that. Stack. Let's set up our test again. Now we should see a fail, hopefully. It might be incredibly slow, maybe. For arbitrarily large textures. Something's up with that. Okay, so let's us that's because it's generating a whole list of them. Let's find one of the first ones, say. Could match type IO list of texture word with list of IO. Oh, it's not actually doing lists. Okay, no problem. That's a small texture. Let's get, say, this texture here. And we'll let X equal that. And we got to import arrays, so let's do that as well. This becomes array from list. Or list array, sorry. List array. Boom. Okay. That's our texture list array. So if we go patterns, what's the texture size of this one? So we know. 6. So if we go patterns of X, size 3 by 3, say. Okay, we get all of those. That should be fine. And the length of that, 16. So that should be 36. Okay, so that's not causing our prop. That shouldn't be causing our prop to hang. This here. Maybe it's just generating really big ones. Maybe we should put like a limit on the size of them to generate. Ah, I'm gonna leave that running for a while to see if it runs out of memory and chokes up my system, or what? If it actually finishes. Okay. So, the way I think we need to change the code in order to make that test pass, if it even runs, is that we can extract the pattern. We can iterate over all of the positions, and then we're going to extract the subpatterns. So for each XY in the whole dang thing, and then we just need to update extract pattern so that the indices here wrap around. On each axis, and that should cover things. We can get rid of none patterns. There. And we're gonna go to texture size. Texture. Yeah. Texture size, texture. And Y up the texture size, texture. Yeah, I already wrote that twice, so. Get those on 2. Yeah. Still not returning anything. And 00 to 55 should be a 6 by 6 texture and have 36 elements in it. Okay, maybe we don't go off the size, the get size parameter of what we're working with. We just generate a texture of some size. Maybe it's just generating too many. We make S, you get a number, a reasonably sized one. We choose int such that it is less than or equal to, say, I'm just gonna pick like 1,000. That S times S. Oh, it lets you choose bound. Okay. I don't need such that. Okay, choose one from size 1 to 1 to 100, say. Cool. There we go. Now we got our failure. Okay, it was just the size parameter was just generating too many of them. Okay, we expected 86. We got way too many. That was not quite the result I was expecting. Okay. The GHCI process is catching up with me here. Okay. Let's close that. There we go. So, let's choose something a little bit more reasonable. Let's say 30. Okay. So that's our input texture. It's quite big. 24. So that's 25 by 25. This is wrong. There should be texture the square of it, not times 2. There we go. Yeah, so a 9 by 9 texture, we should have 81. Alright, but we got way too many. Okay. Well, we did change patterns, so it's all good. Okay. Yeah, I'm gonna undo those changes I did to pattern just to see it fail the right way, and we'll get to. There we go. Yeah, we should have fewer than the expected number. Okay, that's better. Okay, so in order to get that number, we need to go over not num patterns, but the number, the whole range of texture. So if texture is 8 by 8, we should be going 64, up to 64. From 0, 0 to 63, 63. We go up to 4. We're going to go texture size of texture minus 1. Alright, and then we're going to go up 2. There. Okay, so this coordinate here, x, y, is going to be one of those things. The width is going to be our size. The subpattern size we pick here. Okay, and then what were we doing before here? We were accumulating the elements of the source array using a fold. Accumulating the elements from the source texture. Yeah. That's good. Only we go to X, Y, we want X. Yeah, X up to X plus width. Y up to Y plus width. And we want them to wrap around. So, accum elements is where we do our indexing into the source array. So X can be out of bounds here. I think all we need to do is actually make a modulo on the texture, on the size, the width here for A and B. That's my theory. Let's see if it works. And it does. Sweet. Okay, so now we've got that. So let's commit that. That sounds good. Modify patterns. Extract all overlapping subpatterns, or all overlapping patterns from texture. Treating the texture as a toroid / infinite surface. Okay. So that gives us 100 by 100 patterns we can extract from our input source image. We could implement symmetries, and there's like two usually that it works with, which would be like reflection on the one of the planes, and then rotation. That produces different results. Let's just stick with one right now, what we have. Let's just do overlaps. So the other function we're going to need in order to implement the algorithm proper is we're going to need to know what patterns overlap the others in what direction. I think is the gist of it. The source for this, by the way, that I'm working on, that I'm did a bit of research with, is on grid bugs, wave function collapse. They have a really cool article. Gridbugs.org. Paste that in chat there. And it goes pretty in depth into all this stuff. So the pre-processing is where we are right now. We're doing this stuff here. And wrapping around, getting all our tiles. And then we have to we create a tile index and generate some frequency hints and adjacency rules to be given to the algorithm. That's what we're going to be doing. Yeah, so reflection and rotation. So when generating the tiles from an input image, you may want to include tiles which are necessarily present in the input, but which are the rotation or reflection of tiles from the input. So you take one of these tiles, you flip it around a bunch of times, and you got even more tiles. What this does is that from this same source image here, you get, using just the basic overlapping tiles, you get this. But if you do take out all the rotated and images, you get output that looks like that. It's kind of neat. All right. This is here. That's source image. Right, just the tiles you cut out, you get this, with rotations and symmetries added to the sets, or just rotations, it looks like. You can get some other cool patterns like that. So this would be like an input source image with rotations. You can get an output image that looks like that. So we might leave that out for now and get to that later. It wouldn't be too hard to extend it to do that. So let's go right to overlaps, and we'll generate the frequency maps and adjacency rules. Right, so this function here is basically what we need to implement in Haskell, it looks like. Take tile A, tile B in a direction, and returns true if and only if the overlapping, that A is overlapping with B, offset by 1 pixel in the input direction. Okay. We need that, and we need to generate that, and then that, all that stuff. So that one should be pretty straightforward for us to implement. So let's define a type for our directions. Texture stuff, patterns, extraction, we'll start down here. Directions. Or direction. We'll do up, right, down, left. Right. Overlaps takes a pattern of A, pattern of A, a direction, returns a Boolean. How are we going to do that? We're going to case match over direction. Up something, right something, down something, left something. And lambda case. Oh, right and left is going to be reserved. Because it's part of the Haskell prelude. Okay. So it overlaps on, let's just do the upcase, say. P1 and P2. If P1 and P2 overlap, how do we know that they overlap? In the upcase, we're gonna say P1 is the one we're checking if P2 overlaps. So the top rows of P1 and the bottom overlaps with the bottom rows of P2 in the upcase. So if I have, say, in blue, let's do a little thinner. There's my fancy pattern. I got a 3x3 here. That's going to be P1. We're going to check in the upcase if P2 overlaps like this. We know that they're going to be the same size. We can assume that. Right, a little Haddock documentation there. Offset in a given direction. Okay. So in this case here, we have, let's say, we have P1, 0, 0. Change the color. Or let's do 0, 0. That's P1. Right. And let's see, that doesn't overlap with 0, 0 of P2. I know, we can iterate, they're both the same dimension, so we can iterate over all of these indices. And then in the up case, we just need to check these ones here. If in P2 and the top two ones in P1. Got this. So we can do all over some list. No one's going to be in there yet, but let's see. We're going to iterate over X and Y. So some limit. It's going to be pattern width or pattern size. Now we're going to need to get them independently. Yeah. Let's try that. So we get P1 indices. It's going to equal something, and P2 index is going to equal to something. Then if and we need to get the sets of values for those, and we need to check if they're equal. The two sets are equal. So this could actually be P1 values. So A is going to need an eq instance. And okay, we're using list here. It's not the worst thing in the world. Data.list I think has a couple of set functions we could use. Do union. So if we take the difference, and if they're both the same and we took the union, then the union would be the same set as either one. We also do We can zip them together. Takes a function, right? And if we zip together P1 values, P2 values, yeah. There we go. So they should be the same size. Because they're both, P1 and P2 are both the same size. And we zip those together, we get a list of tuples. And then that means our A function here would be both elements of the tuple are equal. There might be a more succinct way to write it, but that's the long way. I can't figure that out because we don't know what P1 and P2 are yet, so don't worry about it. Okay. P1 values. We have to support n-by-n patterns. So we want to start at 0, 0 and go up to size -2. Pattern size -2. P1. And then Y would be pattern size -2. Yeah, as well. And then we want to get the pattern value out there. At P1 and XY. Do the same thing for P2 values, except we use P2. We fix up our syntax. Good, good. Okay, we don't have pattern value defined, but we can define that pretty... Define that, and if we can define that, then we should have the rest. Do patterns. Pattern value takes a pattern A and an int. And returns an A. Although it can't be any arbitrary int, it has to be within scope, so it'd be a maybe A technically. Although we know that these are going to be things, it's just technically we have to. I think we can cap maybe these together safely. That comes with the data.maybe package. Oh, what's the problem there? There it is. P2, P1. Do I have pattern size? I guess I do. Oh yeah, it's just part of the pattern. Okay, so all of these should just be the holes left over. Except type int with word because right, pattern size is word. Okay, that should fix that. Add implement pattern value. Let's go pattern. No, we don't have to destruct that way. We could just do pattern P. But then we just need to index into it. So we go get pattern of P. Array.func. And that is X. We need the X and Y in scope. X times the pattern size of P plus Y. And oh, let's parse input here. Spell that. Maybe I can just import the operator. Oh, okay, and yeah, we need to guard word so that they're in bounds. such that x is less than pattern size, as well as y. Then we can do this access safely, return just. P. Otherwise, nothing for you. God, I need to fix that. And the problem is, yeah, it's just operator precedence problems. And possibly I have them on the wrong side of the bang. Okay, let's get rid of my drawn. That takes the array on the left side, index on the right. Yeah. Oh, we want word. Okay, no problem. Sorry, my C brain was getting ahead of me here. Okay, hold. That's it. Okay. There, now we've got that. Excellent. Okay. So that compiles at least. We should probably have a test for that to make sure that it works. Can we express it as a property? All we can say is that we need two specific patterns in order to see if they're overlapping or not. There's no way we could pick two arbitrary patterns and say anything interesting about overlaps. Although once we implement, that might change once we implement rotate. We can implement rotate, then we can say that for any arbitrary pattern, a pattern rotated twice overlaps with itself in the right, or the right direction, as long as the rotation is 90 degrees clockwise. That kind of thing. So that's what I find with property-based testing, is like, you need more than one function, usually, to get things started. Okay, so let's fill this in. I suspect that this is going to be fairly repetitive and kind of similarly structured. We're just going to change indices. So we might be able to turn this into a function, or like a helper function. But let's just see what the patterns is, and then do that. So let's do up. We did up. Let's do right. Okay, so in the right case, we're going to go all the way down on X. But Y we're going to constrain to... It's like up means P2 is up. So right means P2 should be 1 pixel to the right, or 1 grid space over to the right. Yeah, so what? No, X we're gonna go all the way over. I think up is wrong. Now I'm thinking about it. Yeah, X is going to be limited to in P1 to going to -2, and Y is going to go all the way down, top to bottom. And in P2, X is going to start at 0. No, it's going to start at 1. It's going to go all the way to the end. And Y is going to be top to bottom. Right, so up is actually P2 up 1 pixel. So P1 values are going to be 0. X is going to be all the way to the end. And it's Y that's going to be constrained. We're going to go to 2. And for P2, we need to check at the beginning. X is going to go all the way across. But Y is going to start at 1. And go up to the end. Right, down. So P2 shifted down 1 pixel now. Means that for P1 values, we need to check X all the way across in both cases. But Y is what we need to constrain, so we start lower on X in P1, or on Y, all the way to the end. And this one, P2, yeah, we just go 0 to 1 row before. There we go. And left. P1 values, we're going to be constrained on X, so Y is going to be the same in both cases. And X here is going to be P2 shift over to the left, so P1 is going to be from 0 up to 1 column before. And on P2, it's going to be starting 1 up to the end. Haskell's already complaining about my duplication. Okay, so that's overlaps. Let's clean it up a little bit, I guess. This function here, I wonder if there is a function for that already. Let's Google that one. I guess if they're equal AA, then it's already true. Trivially. Okay. Well, whatever. If anybody on watching knows what it should be, just let me know and I'll throw it in there. Otherwise, I'm just gonna write this as a quick little helper. Or maybe I can just put in a where clause. Grab you all. So this one is repeated. Here, so left and right. Should that be right? So, we shift right. P1 should be going from 0 to, yeah, P1 minus 2. And P2 just needs to go from... No, P2 needs to go from 0 up to P1 minus 2. Has to be P2. P2, 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 even though they're the same. Does it have to be? Okay, so in the left case, boom, right. This should be 1 to P1 minus 2. This one should be 0. 2. There, yeah. That's interesting. In the right case, X here and P2. We need to go from the 0th column up to the middle, whatever, just before the last column. And if we shift P2 to the right by 1, that's still true. It's still the same. For some reason I expect them to be different. I don't know why. Yeah, it makes sense. Alright. P1. P2. Shifted to the right. Right, we want this area here. Alright, so we want to start from 0 up to whatever the size minus 1. And in the other case, right, we got P1 and P2 over here. Right, we want this area here. Ah, it should be different. So we want to start at, yeah, okay, that's better. That's what I thought. Alright. Gotta go with your gut sometimes, your instincts, you know what I'm saying? You're gonna start at 1. And we actually have to go up to the end on P1, or P2. There we go. Sweet. Okay. Let's see. Is there... We could at least write a couple of unit tests just to at least convince ourselves that it's probably right. Like I said, maybe we'll get into symmetries and rotating the patterns later, then we can write property tests, which would be a lot more stronger. Once we do that, because I can figure how we could write a pattern for a property test for overlaps in relation to, say, the rotation symmetry, because then we'll have to generate one arbitrary instance, and then we can make that relation over the two. But overlaps on its own, we can't pick two arbitrary tiles and overlaps. Like, they gotta be themselves. I guess the... yeah. Let's just stick with the unit test idea for now. Describe overlaps. And we're going to say it could return true. Or overlapping patterns. So I guess one thing we could say is for each direction, the fill pattern will always overlap with itself. So we could say context given a fill pattern. It should always overlap with itself in every direction. And we get the list of directions. Up, right, down, left, or in those directions. We should say fill pattern, make fill pattern, and we need an element to make 0. We have scope type variables already in there, so we'll just do it like this. 0, it's going to be an int, I swear. Because I'm going to use literals for a word, and that'll be 1, 1, or make it 3, 3. So, overlaps. Fill pattern. The fill pattern. And direction could satisfy. is just... I gotta import that from data.maybe. And the survey says not compiling yet. Because I need to import it in scope. From for control.line. Could type maybe 0 with bool. Oh, overlaps returns it. Right. Make fill pattern returns a maybe. That's what I was thinking. This should be true. And we know this is going to return a pattern, so I'm just going to pull it apart because it's just test code. This kind of assignment you probably shouldn't do, but test code is test code. In the pattern binding, trying to get a little tricky here, a little clever. Too many arguments. Yeah. It's gonna annoy me with that. But... I can turn that off in the test module. Okay. So that passes. And known overlapping patterns. Given some known overlapping patterns. Good overlap. Make P1 equal something. P2 equals something. Then we should be able to say overlaps. Let's make the example, I don't know, up. Okay, and the way we are going to construct that pattern is we're gonna have a function. Right. It's going to take a list of A and return a pattern of A. If you give me the empty list, you're going to have a fun time. That's why I'm calling it unsafe. Okay, so we know we need to return a pattern. It's going to be the length of x's. No. Scratch that. It's not going to be the length of x's. You have to give me a square list of values. Or you give me the indices and the value. Really made this tricky for myself. Let's just hard-code it in with the constructor, whatever. So we want to do a 3x3 pattern. And then we need to use array. Construct that. Okay, data.array. Qualified. Array. And then we know we could do array, list array from 0, 0 to 2, 2. Do that there. Okay. So for P1, we'll do at 0, 0, we'll do 1 row of 1s. And we'll do the same thing for the next row. Sorry, it's 0, 1, 0, 2, 0. It will be 1. I'm not sorting them. They'll be usually they're sorted lexicographically when they get printed out, but I'm just going to make them not that order. I don't think it'll matter. Okay, 2, 1. And the final row. 0, 2. 2. And 2, 2. Okay. So we want this one to be, I don't know, we'll make this like 3s on the bottom row here. And we'll do the same for P2. Except, we'll make the bottom rows ones as well. And the top rows 3. Doesn't really matter what they are, but... Might have implemented things correctly. Sorry, post positive, because my brain. And package. Gotta add array here. What was that warning? Oh, because we're using 3 here. Haskell doesn't know it's an integer. Could be some other num class. It's just a defaulting type warning. Oh, sorry, not 3 int. That is a word. The arrays. I think we use type applications here. Make that go. This is an application for constructors, so I think that should work. We probably need to implement. Enable type applications. And there we go. Yeah, so the warning's gone away. That's good, right? Like that. But yeah, so it's failing. This element here. Oh, jeez. What is this? Oh, we don't need to give the indices. Ah, my bad. That's gonna be tricky. Are they gonna be in the same order that I'm expecting them to be in? The test. Oops. There we go. Okay. Okay. Yeah, it's probably not in the right order that I think it is. Let's get rid of data.maybe because we don't need it. Okay. Let's see. Is it down? Oh, this is going to be... So this one's going to be at 0, 0. That's going to be 0, 1 and 0, 2, I think. Yeah, so at 0, 0, we're going to want, for P1, we're going to want 1. We had a 0, 2, 1, or 0, 0, 1, 0, 2, 0. This would be 0, 0, 1, 0. I think that'll be this one, actually. And this would be 0, 2. If we just rotate them a little bit. And these should be 1. That one. Yeah. Okay, okay. Good, good. So it's kind of a trivial test, but at least that one works. Should overlap on up. It should not overlap on the others. Alright, so let's move these into our context. Okay, 2, line you back up. There we go. And then for not up, so right, down, and left. Overlaps. P1, P2, direction. Could it be false? Okay, good stuff. All right, so we're a little over time this week, but that's okay. What does this want us to clean up here? Take the parentheses off of length. I see I had it on there for a reason. Okay. Okay, so that's in a good place. Let's commit that. Add overlaps. Checks if two patterns overlap offset when two patterns, P1 and P2, overlap when P2 is offset by 1 in the direction specified. Okey-dokey. So, there we go. Do we have... I don't have a repo over this one yet. So, I will make good on my promise and I'll post a repo. And we'll push this code up. Thanks for tuning in and following along. And hanging out. If you want to follow me on the socials, you can find me on the Mastodon on the Fediverse. You can find me on Mastodon in the Fediverse there. It's types.pl, that's the server. I'm Agent Ultra. And you can find me there. You can find me on GitHub as well at Agent Ultra and all the places for the most part. But links in my bio there too. So there you go. What else? I do these streams once a week on Tuesday evenings, about 10 after 8 in the Eastern time zone. So you can write that down, or if you're on the Twitch or you're watching on YouTube's, you can, you know, do what you do there and subscribe, follow, all that kind of stuff, and then you'll get notified when I go online. And then you don't have to write it down. Pretty convenient, that. So what else? That's it. That's all I got. Oh, no, go to the link above. There's also a link to a Discord server. If you're on Discord and you want to chat, couldn't ask a question on the live stream, if you follow on YouTube, you can ask your questions there. I'm usually hanging around there, and we'll answer your questions. Or you can talk about whatever you want to talk about. What you saw on stream, your own projects, things like that. And I think that's probably about it. So thanks for tuning in again. May all your monas be free and your types always check. And we'll see you next week. Take care. Stream over.